activate protein kinase A through a mechanism that we won't discuss now. Now, this action is done on adipocytes. So you notice here that this cell on which this is occurring is an adipocyte. And in the adipocyte, we have large storages of triacylglycerol. That's what this lipid droplet is right here. In the lipid droplet, there are large quantities of triacylglycerol. And certainly, if you need more help with this part of the video, certainly go review the lipid oxidation playlist. But suffice it to say, cyclic AMP switches activate protein kinase A. Protein kinase A has two primary targets. Number one, it has a target called a paralipid. Paralipids are these proteins that exist on the surface of the lipid droplet. And normally at rest, in the inactivated state, the paralipids have a protein that's attached. And that protein that's attached is called CG1. Okay? While bound to the paralipid, CG1 remains inactivated. Okay? The second target of protein kinase A is this enzyme called hormone-sensitive lipase. This is a simple serine hydrolase that will see the mechanism of in just a minute. Okay? When the paralipid is phosphorylated, CG1 dissociates from it and activates an enzyme called adipocyte triacylglycerol lipase. Adipocyte triacylglycerol lipase catalyzes the irreversible hydrolysis of one of the fatty acids off of triacylglycerol to make a diacylglycerol. In other words, the reaction of adipocyte triacylglycerol lipase is one triacylglycerol to one diacylglycerol and one free fatty acid. Okay? We'll look at the state of the fatty acids in just a moment. Now we have a diacylglycerol. The newly activated hormone-sensitive lipase, in other words, the hormone-sensitive lipase with the phosphate, can now act on diacylglycerol, and it irreversibly converts the diacylglycerol into a monoacylglycerol and a free fatty acid. In other words, hormone-sensitive lipase in its activated form hydrolyzes off the fatty acid from diacylglycerol, generating monoacylglycerol. And the terminal lipase, monoacylglycerol lipase, this is going to catalyze the irreversible hydrolysis of a fatty acid off of monoacylglycerol. This is going to generate glycerol, which will ultimately leave the adipocyte and enter the bloodstream, as will the free fatty acids that we generated from complete hydrolysis of the triacylglycerol. And for this video, what we're going to assume is that the triacylglycerol has three saturated fatty acids. Okay? Of course, we can deal with unsaturated fatty acids, but for simplicity, it's easier to conceptualize the saturated fatty acids. Okay, and those saturated fatty acids and the glycerol will enter the bloodstream and go to the liver. The glycerol will ultimately be shunted into gluconeogenesis, and the fatty acids will be run into beta oxidation. But to understand this, we need to understand one thing prior to that. Okay, so at this point, what we're assuming is that the fatty acid has entered the liver cells. Okay, it's traveled through the bloodstream, bound to serum albumin, and when it gets to the liver cell, it gets transported through the membrane, and now it's in the cytosol. Well, now we have this enzyme called fatty acyl-CoA synthetase, which is going to effectively ligate the fatty acid onto coenzyme A. And so what we should get at the end of this reaction is something referred to as a fatty acyl-CoA. Okay, like I said, this is simply a fatty acid ligated to a coenzyme A in a thioester bond. And we note that thioester bond right here, which is characteristic of fatty acyl-CoA. The fatty acyl-CoA can then go into beta oxidation. Just bear in mind that during times of fasting, the liver cells are deriving most of their energy from beta oxidation. Let's explore how they do that right now. Essentially, what's going to happen in beta oxidation is the fatty acyl-CoA derivative is going to go through several rounds of beta oxidation. In each round of beta oxidation, what you're going to generate is one totally reduced coenzyme Q. This is generated through the action of